So for test number 4, the only mathematical problem that you'll have for from chapter 19 is this type of phase change reaction where we're going to calculate the change in entropy for a given amount of a sample. So if we look at this problem, we're dealing with water, okay, and we know that it melts at 0 degrees Celsius. Melting, so we're just talking about going from a solid to a liquid, so where it's an ice cube melting. And that ice cube weighs 25 grams. The enthalpy of fusion is given to us here at 6 kilojoules per mole. And that's describing the amount of heat that's associated with, well, that kind of change, going from a solid to a liquid. Now, what we have to realize here, there's a couple of aspects that to keep track of. We want to calculate the change in entropy for this system. And whenever we're talking about a phase change, there's a particular equation that we use here. And it is the change in the enthalpy for this reversible process. Remember, reversible processes are kind of an idealized system. Phase change is really the only place we apply that, any kind of, to any extent in this class. And, well, besides maybe a little bit of conceptual stuff. And it's just the enthalpy divided by temperature. And just remember, what is this going to give us? Once we plug and chug this is going to give us a unit of joules per Kelvin, which is what our, or kilojoules per Kelvin. It just depends on the magnitude of the change. But that's the units of the entropy value, okay? Now, the temperature portion is the easiest one to do, so let's just do that. 0 degrees Celsius, well, if I want to convert that to Kelvin, it is, the Celsius value plus 273. And so the temperature value is 273 Kelvin here. Just like we've seen in many examples in chemistry, we always want to use Kelvin whenever we see temperature in a formula here. Now, the enthalpy change for this process is a little bit more difficult to figure out. So let's take a look at it. Now, this particular value of enthalpy, or the heat change, right? We sort of use those two terms casually, interchangeably. Just know that they're not exactly the same. It's not particularly important for us. But the heat change value that we see here, right, this is the amount of heat per mole of the sample. And with 25 grams of ice, that's going to be more than 1 mole of ice. So what we're going to see is it's going to be something larger than, if it's 6 kilojoules per mole and we got more than 1 mole here, then the amount of heat that's actually gained during this process is going to be more than 6 kilojoules. And you can see that in the mathematics. So let's just do this calculation here. So here we want to calculate the delta H portion. And I'm just going to do this as some kind of just a regular kind of Gen Chem 1 dimensional analysis calculation. This is really something that you first saw back in chapter 5 for Gen Chem 1. And we have the mass of the sample. And just like we've seen a few times, when in doubt, calculate moles. I'm looking at this value here, and grams is not present in that expression. Moles is. That suggests that the first thing I want to do is calculate the number of moles in this 25 gram sample. And the way to do that is we are going to divide by the molar mass of the sample. The reason why we do that is because if we divide by the molar mass, grams cancel out and we're left with the moles. And then we can come up here and use this value as really in this dimensional analysis expression to then calculate the amount of heat that's associated with this particular amount of the substance. And then what that's going to look like is that I'm going to multiply now by the 6 kilojoules per mole. And why do I do that? Well, because I want moles, to cancel out. So mathematically, what I'm doing here is 25 divided by 18.02 times 6, and that gives me 8.3 kilojoules. And that's the amount of heat that back in 151 we expressed that as Q. That's the amount of heat that this ice cube has to absorb before it fully melts. And this is going to be our delta H for this reversible process. And we do the math here, and we see that it comes in at a fairly small amount, which isn't unusual for entropy. I'm going to convert that to joules. It comes in at 30 joules per Kelvin. And that's your final answer. So it tells us there has been an entropy change of 30 joules per Kelvin. This is a positive value. Okay, now you don't have to write that in there, right? The positive portion is always implied whenever you see a number like this. But I just want to just sort of come full circle with a few topics that we've talked about in class. You know, we have a positive delta S here because we're having a phase change going to a liquid state. In class, we talked about going from solid to liquid to gas. Each step, there's an increase in the entropy of the system. And that just confirms what we already know. So one thing is that when you're looking at an answer like this, it doesn't make sense in the context of the problem. And in this case, it does. So this positive entropy change is telling us that there's the energy associated with this system when it goes in the liquid state is now more dispersed. The energy states are more random. There's more different ways that we can arrange the molecules, if you will, which is consistent with our notion of entropy, our understanding of entropy. Now, for this little test review, I also threw in a couple other additional questions just to touch base on some other topics here. And since we're talking about phase change, not just can we, describe the entropy change, but we can also talk about the heat associated with that process. If I'm talking about ice melting, which I am here, and we actually see it here, okay, it's gaining a certain amount of heat. That is an endothermic process. The reverse process, going from a liquid to a solid, freezing process, well, remember the nice thing about heat and enthalpy is that if you're talking about the same quantity and the same process, the reverse of that is just the negative. Or in this case, conceptually, what that means is that heat is going to flow out of the system now. So this is an exothermic process. And if I wanted to describe if I wanted to talk, at least with using this equation for entropy, the freezing, I'm not going to write it in the notes here because I don't want to get it sort of more cluttered than it is, but the change in entropy for the freezing process, if we think about it as a reversible, if we think about the system as being reversible, then it would be a negative 30 joules per Kelvin. Now, that plus and minus change for the entropy value is really only true for a reversible process, not for your typical irreversible process. And that deals with other topics, so I won't get into that here.